So as a brief introduction, I'm a student at the moment. I have theoretically done this project since my honours year. I've been looking at the effects of elevated temperature on the KwaZulu-Natal Sandstone Sourveld, what Richard Boone said earlier during the presentation to all of us. I'm pretty much building on that as one of their students. And this project's currently my master's project. Okay, so I guess to begin, good afternoon everyone, or pretty much good evening by now. So I'll be introducing our study on the effects of simulated elevated temperature on the KwaZulu-Natal Sandstone Sourveld vegetation. This study is linked with the eThekwini municipality in a joint research partnership with the University of KwaZulu-Natal. This program offers transdisciplinary research on urban biodiversity, people and climate change within the Durban area, and is focused on the KwaZulu-Natal Sandstone Sourveld grasslands. We aim to inform the implementation of sustainable land use planning, biodiversity conservation, environmental management, and climate change adaptation practices, while also contributing to the development of capacity in these areas of expertise. With that said, I will be providing more information on the KwaZulu-Natal Sandstone Sourveld in a little while later. To provide a bit of background to what the study was about and what it went out to answer, we'll have to start at the effects of climate change. Increasing global temperatures to a degree of 1 to 5 degrees Celsius, rising sea levels, and the common occurrence of more severe storms are predicted to become more prevalent within the next century. However, in this study, we just focused on one of the effects of climate change, the increase in global temperature. Physiologically, plants respond in varying degrees when exposed to elevated temperatures. The initial increase in temperature is compensated for by evaporative cooling in the leaves, which can lead to water stress over extended periods of time. Photoinhibition is another problem, as it can occur if they experience temperatures over 45 degrees Celsius. This can affect the plant's photosynthesis, and with the decreased photosynthesis comes a reduction in the plant's productivity, which can then cause an influence on the community structure or composition in which it occurs. These effects are, however, not universal across all plants. This is because C3 and C4 plants show different responses to an increase in temperature. C4 plants being mainly grasses, while C3 plants being mainly broadleaf trees, forbs, or shrubs. They both have different photosynthetic pathways, which are linked to the difference in their respective leaf anatomies. The difference plays a part in how they will respond to an increase in temperature, with C4 plants being predicted to favor the warmer conditions. In this study, we focused on the grassland biome, specifically the KwaZulu-Natal Sandstone Sourveld, and how this vegetation will actually respond to elevated temperature. The grassland biome is under great threat from urbanization, industrialization, as well as afforestation, creating a fragmented landscape with rapidly declining areas of this rich biodiverse biome. Presently in South Africa, only about 2.8% of our grassland biomes have been placed under conservation, with the KwaZulu-Natal Sandstone Sourveld being nationally listed as endangered due to its high transformation. Presently, only about 11.4% of this vegetation type remains in its natural state, with only 0.1% formally placed under protection, as Richard said earlier. Yet we still know very little about its biodiversity or ecology and what management strategies need to be implemented to preserve this grassland. Sadly, the total remaining KwaZulu-Natal Sandstone Sourveld in the eThekwini area is already below the conservation target of 3,920 hectares. Thus, to aid in the conservation and management of the remaining KwaZulu-Natal Sandstone Sourveld, we need to know the possible effects under various climate change scenarios. Which is why we have set this aim for the present study, to investigate the vegetation responses to simulated elevated temperature in a subtropical grassland, such as the KwaZulu-Natal Sandstone Sourveld. In order to achieve this, we needed to conduct floristic studies, understand seasonal responses, and then link the environmental data to the vegetation responses. To undergo this study, I constructed open-top chambers from a design I had modified from the International Tundra experiment. The chambers were constructed from clear 2mm Naxal polycarbonate sheeting with a support structure made from 20mm conduit tubing. The study site that I used for this project is a remnant patch of KwaZulu-Natal Sandstone Sourveld, within the Durban area, called the Tanglewood Nature Reserve, which is privately owned. The methodologies adapted for this study was that I used 5 open-top chamber and control plots, which were run per season over a single year. Environmental parameters such as soil moisture content, humidity, light intensity, as well as temperature, which were taken weekly at midday through the use of a handheld weather station, as well as hourly temperature data collected through eye-button thermochrons, which are temperature loggers pretty much. These thermochrons were placed at various locations, 15 centimeters above and 5 centimeters below ground within each open-top chamber and control plot. Species diversity, composition, as well as abundance were collected as floristic data, and productivity was determined through the use of looking at the above and below ground biomass. However, in this presentation, I am only going to be talking on species composition and above ground biomass or productivity. I've placed the seasonal dates at which I ran this project over on screen. These figures represent the average seasonal above and below ground temperatures collected with the thermochrons throughout the experimental period. I want you to pay attention to the lines in red, which actually aren't that clear. The lines in red, pretty much all the ones on top are the lines in red. I want you to pay attention to these lines in red as they represent the elevated temperatures simulated by the open-top chambers. The midday peak in temperature can be clearly seen here, as well as a much more stable soil temperature. Soil temperature, and then these are my above ground, so below ground and above ground temperatures. The midday, to determine significance, the day was divided up into 3-hour periods, as seen by the light grey lines. All open-top chambers showed a significantly higher temperature increase in above and below ground, except for the above ground readings at 6 a.m. to 9 a.m. In autumn and 9 p.m. to 6 a.m. in spring. These open-top chambers were able to simulate an increase of between 1.3 to 2.4 degrees Celsius above ground and 0.7 to 1.3 degrees Celsius below ground during the day, which was classified from 6 a.m. to 6 p.m. While at night, 6 p.m. to 6 a.m., an increase of between 0.3 to 0.7 degrees Celsius above ground and 0.5 to 1.3 degrees Celsius below ground was simulated. I'll quickly go over the other environmental data that was collected in monitoring the effects of the open-top chambers at simulating elevated temperature. This data was collected to help validate the hourly temperature data collected by the thermochrons. The figures here represent the mean midday temperature for each season. This data was collected at midday through the use of the handheld weather station positioned 25 centimeters above the ground level. These results showed that the open-top chambers had a significantly greater temperature within each season. As it is seen in the literature, with an increase in temperature, there will be a subsequent decrease in relative humidity. Thankfully, my figures support this, with the ambient temperature in the control plots being significantly greater than the elevated temperatures within the open-top chambers, in all but the winter season, which is most probably due to the decreased rainfall over this period of the year. From here on, I will be referring to the control plots as ambient temperature and the open-top chamber plots as elevated temperature to avoid confusion. The soil moisture content shows a similar pattern as that of humidity. With an increase in temperature, you get a subsequent decline in the soil moisture content. Elevated temperatures in all seasons show a significantly lower soil moisture content when compared to the ambient temperatures. It also must be noted that the values labeled as natural on these graphs represent the undisturbed natural grassland without having disked or cut the soil down to the ground level. Interestingly, the natural grassland and ambient temperature values are similar during the winter seasons, or the wetter seasons, but vary when there is a reduction in the rainfall over the autumn and winter months. This is probably explained through the increase in evaporation from the soil surface after the above-ground vegetation was removed at the onset of each season. The open-top chambers appear to have a negative effect on the mean light intensity, with significantly lower values during spring and winter. However, it must be noted that the standard deviations are extremely large on the open-top chamber readings. This is through the polycarbonate having a slight shading and magnifying effect as the sun rises and falls each day. Moving on to the floristic data collected at the end of each season. It is great to see that the species compositions are corresponding to each season as one would expect. The winter months appear to have the lowest number in species. The spring months have the highest, while the summer and autumn months are somewhere in the middle. Spring most probably has the highest species composition due to its increase in temperature, causing the overwintering species to germinate or increase in biomass production. Although no significant difference was found in species composition throughout the year, there does appear to be a decline in the number of forb species within the open-top chambers during spring, summer, and autumn, which is most probably due to the increase in temperatures causing a subsequent increase in the productivity of the graminoid species within these chambers. Ooh, sorry. No, never mind. This figure represents the mean above-ground biomass production. This data was collected by harvesting all vegetation, be it graminoids, forbs, or shrubs, that were grown inside the open-top chamber and control plots. As earlier mentioned, all vegetation was initially cut down to ground level, allowing for the actual growth of the life forms to be determined at the end of each season. It is clear that the major growing seasons in the sandstone sulfur are spring and summer, with very little growth occurring in the cooler months of the year. There is, however, a clear difference between the above-ground biomass production in the graminoids within each season, with the exception of winter. But there was no significant variation in the biomass when comparing the elevated and ambient temperatures. Although in spring, the above-ground biomass of the graminoids within the elevated temperatures of the open-top chambers had a p-value only marginally greater than 0.05. There was no significant difference in the above-ground biomass production in any of the other life forms within each season. But it can still be seen that the mean above-ground biomass production in the graminoids within the elevated temperatures were slightly greater than those found within the ambient temperatures. When looking at the total above-ground biomass, it can be seen that there was a significantly higher biomass production within the elevated temperatures of the open-top chambers within spring. Thus, it is clear that the graminoids are the main contributor to the total above-ground biomass, especially in the warmer seasons, as one would expect working in grassland. So to sum it up, the open-top chambers appear to be able to simulate a realistic elevated temperature that we are likely to see in the future. However, this appeared to be causing a subsequent decline in both the humidity and soil moisture content. Whilst this could be an artifact of the chambers, it is predicted that we will see these same effects with elevated temperature in the future. Therefore, these chamber effects need to be taken into consideration when interpreting the floristic results that were collected from this study. The effects of elevated temperature on the vegetation were particularly evident when the above-ground biomass production of the graminoids were compared, with the mean biomass of the graminoids being greater in the elevated temperatures during the spring, summer, and autumn. Even with no significant changes in species composition when subject to elevated temperatures, there appears to be a decline in the number of forb species under these conditions, which we hypothesize is due to the increased biomass production of the graminoids. However, for me, the study doesn't end here. We intend to dive deeper into the floristic responses by looking at the changes in abundance, below-ground biomass production, variations in C3 and C4 species, biochemical assays to determine possible grassland indicator species for elevated temperature, as well as doing another year of replication. Also, please do understand that this is only a short-term study, and further long-term studies do need to be taken out.